Okay. Okay, we can start our session, and our speaker Volodya Rubtsov from so many cities and Angers, Moscow, and Trieste. With talk about Monge-Ampère equations. The second lecture about Monge-Ampère equations will be in this seminar in April 28. And now, Volodya, you can start.
Yes.
Okay.
Okay. Thank you. Thank you very much. First of all, I'm very grateful to organizers of the seminar to give me this opportunity to speak. And also, traditionally, I will start with some excuses. And this time, my excuse for probably not original kind of my talk, because 2 years ago, I gave a talk very similar, maybe not identical, but very similar in Moscow Beijing colloquium, and probably some of potential participants attended this talk. So for them, it will be nothing new. But I think that this talk, I don't pretend to be very original about the results, though some results may be unknown to wide audience. My aim just to give an introduction to a series of talks with really new and sometimes exciting results, which we obtained in cooperation with Professor Rubtsov, Wolf from University of Surrey in Guildford, UK, and two young students, PhD students, Roberto D'Onofrio, Lewis Napier. They are both students in Milano and in Surrey. Lewis and Roberto, both Milano and Surrey. And in Milano, our collaborator in one of this series of papers, my old friend Giovanni Artenzi, he's co-advisor of Roberto, and the next talk will be exactly Roberto. So we want to present all aspects of this application, and my introductive talk will just give some easy way to explain what interesting things you can wait in the next talks. Singularities and pseudo-Riemannian geometry, very rich Riemannian and higher structure geometry in the future talk of Martin Wolf, and very interesting hydrodynamical and meteorological application in talks of Jan Rulston and Lewis, which will be after. Now I start. So we will speak about Monge-Ampère equations, Monge-Ampère operators. This approach to Monge-Ampère operators was proposed at the end of '70s by Valentin Lychagin, my teacher and colleague in Vinogradov seminar. I remember his first talks in Vinogradov seminar, really excited reaction of people, because it was absolutely fresh and new at that moment. But of course, it would be impossible without previous work. French geometric school of E.Cartan and his student Théophile Lepage, who was a Belgian academician, and he wrote a thesis about some symplectic geometry of exterior forms. But Valentin rediscovered this Lepage approach. Finally, he found the initial paper, but Lepage didn't apply results to differential equations. It was completely know-how of Valentin Lychagin. Then I will discuss what we can do with this approach, namely how we can get self-similar solutions and probably some other interesting things with Monge-Ampère equation and Monge-Ampère operators. And mainly this approach was showed that it is very, very rich applications in the so-called classification problem. It was classical problem which Sophus-Lee 1874. Sophus-Lee supposed classical Monge-Ampère equation with two independent variables can be always linearized by so-called contact transformation. In fact, it is almost true. It means his conjecture was almost true, but it is not completely true. And we proved with Valentin Lychagin in '82 that this equation might be only quasi-linearized, not linearized, and only what our proof was we succeed to give this proof only in analytic coefficient case, not for C infinity. I will at the moment I will not sure that all arguments are working very well for C infinity. And then we went further. We considered classification problem in 3 dimensions, and it was completely out of Sophus-Lee vision, and we showed that in 3 dimensions it is still possible to classify Monge-Ampère equations by with respect to symplectic and with respect to contact transformation, but in contrast to 2-dimensional case, they are not linearizable even in the point. If in the case of 2D in the point, equations with constant coefficients can be linearized in 3 dimensions, they are not linear in the main orbit of the action of symplectic diffeomorphism and contact diffeomorphism, probably. But out of dimension 4, I will not go today, because out of dimension 4 there are no discrete moduli problem, and this problem classification of Monge equation is solved partially. By the way, I want to mention another approach to classification of symplectic Monge-Ampère equation, which was proposed by Evgeny Feropontov, Boris Kruglikov, and Boris Dubrov. They proposed classification of symplectic Monge-Ampère equation in some case in some transversal way to our approach. It is not exactly the same notion of classification. They classified the Monge-Ampère equation from the viewpoint of hydrodynamic systems, and it is different classification. And funny story is that our equations, which are non-linear, from the viewpoint of their classifications, they are not interesting, and their interesting equations are not interesting from the viewpoint of our classification, because we also have some classification results, traditional classification results. So these two approaches, in some sense, transversal. They are complementary one to another. Intersection is very, very short, but this short intersection is physically is important. It's so-called Klebanski equations in 4 dimensions. That's some kind of prospect of our studies. And now I will show you a cat. This cat, his name is Eureka. He will go with me through this talk. And this cat from our book, it means that it is something really important in this page, on the page with this cat. Oops, sorry. So this, I remind you what I am speaking about. I'm speaking about Monge-Ampère equation. It's in 2D, this equation with two independent variables, Q1, Q2. Traditionally, it's notation from classical mechanics. And this equation is second order, and this equation is linear means that it is not very non-linear of special type non-linearity. This non-linearity is given by determinant of Hess symmetrics of unknown function f. So our unknown function of Q1, Q2 satisfies this equation, and second order part contains linear part, this linear quadric A, B, C as coefficients of the quadric, and D is coefficient in front of this Hessian determinant. Plus E, it's a free term, and A, B, C, D, E, I will suppose simply dependent on and first derivatives of f. So all quasi-linear
for interruption.
cases are, yeah.
But probably could you switch off your video because your audio is freezing? Could you please switch off your video?
My video?
Yeah, probably it's better to switch it off because we cannot hear you properly.
I see. But what switch off
Yeah, switch off the video.
one?
Okay.
Is it okay?
It becomes better. Yeah.
Okay. So I'm sorry. It's you see, it's the connection from my my office. It's a official university connection. I can do nothing. It's not anyway. So did you understand the conditions on the equation? This is a classical Monge-Ampère equation, and Monge and Ampère they consider this equation in quite different situation and with different aims. Monge considered this equation in geometry. His first example of such equation was the equation of a curvature of surface embedded in R3. So if you impose condition of constant curvature, you'll find global solutions which Monge discovered, sphere and pseudosphere, for different kinds of your curvature. But what about Ampère? Ampère was in fact inventor of the first self-similar solutions for Monge-Ampère equation. Namely, he solved the equation with the help of so-called Legendre transformation. So Legendre transformation for Monge-Ampère equation, they were introduced by Ampère in his paper in the École Polytechnique journal. It is in very good correspondence with Arnold theorem that there are no notions, no theorems which carries some name, and these names has nothing with the subject of the theorem. So Legendre transformation was introduced by Ampère, and equation was introduced by Monge. Anyway, we will introduce also notion structure just to consider some interesting geometric application. First of all, I want to say that probably mainly because of lack of time, I will speak about so-called symplectic Monge-Ampère equation. For me, it means that if you have this equation, these coefficients A, B, C, D, and E, they are not explicitly depend on unknown function f, and only depend on their partial derivatives. This equation I will call symplectic Monge-Ampère equation, but I want to say that the whole theory extends immediately to full Monge-Ampère equation if you consider, instead of symplectic structure, contact structure, and the classification results and it's about self-similarity and results about symmetry and conservation laws. They are obtained in the full generality for both symplectic and contact cases. Today, I will concentrate on symplectic part of the story. So under the Monge-Ampère structure, I will understand the structure on even dimensional manifold X. The main example of this, of course, will be cotangent space of some smooth manifold, because all theory, I want to stress from the very beginning, the all theory is local. So for me, any symplectic manifold, it's more or less T star of X, or even space and then. And under Monge structure, I will understand the couple big omega, small omega of canonical symplectic form, big omega, and n form, small omega, n form where n is a half dimension of our manifold X. And additionally, I will consider condition of skew orthogonality of this form small omega. And this skew orthogonality condition, I will call effectiveness condition. So for form omega small is omega big effective. So if I have a couple of such forms, I will speak about Monge-Ampère structure on the even dimensional manifold X. What is the main idea of a Lychagin approach? I will try to explain it in the following simple way. Let's consider big.
Volodymyr, is it the same as Lagrangian fibration?
Yes. If you will see Lagrangian fibration, you will see. Just a moment. Just a moment. This is the main idea with Lagrangian fibration. Yes. Let's consider just a vector function big F from R to N to R to N. Sometimes I will suppose that we have a complex, additionally complex structure, but it is now it is not important, this I. You can forget about it. And then we consider the graph of this vector function. Vector function, of course, is a subspace in cotangent space to Rn, which is R2 times n, split it on two parts. And then if I take this graph and take a point of this graph, x, big F of x, then tangent space to this graph is the graph of its differential, I mean differential of F at the point x. And then I have a question. When this graph is a Lagrangian subspace in T star of R to N? In fact, it is immediately easy to see that it is true if and only if the differential at x. And it means that the Jacobian of my transformation big F is a symmetric matrix. And this is true if and only if the form, one form with coefficients big F sub I is closed. Because we have everything in R to N, closedness means that it is equivalent to exactness of this form. It means that there is a potential small f such each coordinate of F sub I is the partial derivative of F. It means that our vector function is the gradient of this potential. So you see that if we take now projection of the graph of this gradient, of the graph of D d small f, projection on x part of R to n, in coordinates, it gives you the matrix, Hessian metric, which is a main nonlinearity of Monge-Ampère. It means that we have geometric interpretation of our future Monge-Ampère operators. Formally speaking, now, what is the Monge-Ampère operator, symplectic Monge-Ampère operator? This operator acts from smooth functions on given n-dimensional manifold to top forms on this manifold, and defines in the following way. We take any function f on M, we take differential gradient, whatever you want, we consider it like a section of cotangent T star of M, and we consider restriction of our form omega on the graph of this differential top form on M. So we can consider function which is in front of this top form, in front of the volume form, and this is the image of F under this operator. So we can consider Monge-Ampère operator defining in such invariant way, like operator from function to function, which usually people in differential equation suppose. Let's consider some examples. First, if we have a form as a manifold, I will consider R2 with coordinates Q1, Q2. P star has coordinates Q1, Q2, P1, P2. Let's consider two form dq1 wedge dp2 minus dq2 wedge dp1. What is the restriction of this form to the graph of differential sum function f? It means that we should replace P2 and P1 by the corresponding partial derivatives df over dq2, df over dq1. Then derivatives by q1 here and q2 here, they will disappear because of wedge product. So from the first two form, we will have d2f over dq2 twicely. And here we have d2f over dq1 twicely. And then reducing the similar terms with the proper sign, we obtain Laplacian of f in front of the volume dq1, dq2. So as operator, we have Laplacian operator. As equation, we have Laplacian equation. Similarly, we have hyperbolic analog of Laplacian, wave or D'Alembertian operator, taking this form with plus. In 3 dimensions, we have main interesting operator Hess of f. I will denote by Hess, not Hessian, but determinant of Hessian. So it is a operator of second order operator. Three variables Q1, Q2, Q3, and restriction on the graph gives you instead of P1, P2, P3, you take partial derivatives and you obtain Hessian of f, and one comes from this one in front of this volume form in R3. So this 3 form give you Hessian minus 1. So it is equation Hessian f equal to 1, which is given by this restriction on the graph. And interesting equation, which is very important in modern physics, which is called special Lagrangian equation. Its equation Laplacian equal to Hessian dimensions is given by the following form. You have form P1, Q2, Q3. After restriction, you obtain here only derivative by Q1. Here, only derivative by Q2. Here, only derivative by Q3. This gives you Laplacian. and this dp gives you Hessian. So it is special Lagrangian. It is very important for so-called calibration geometry, and it is also very important ingredient of so-called Strominger-Gauss-Zaslav mirror conjecture. I will not speak about it here. Okay, now what shall we do with this correspondence? First of all, I want to say something important. Be careful, this correspondence has a huge kernel. It means that if you have this definition, and you take as a form, for example, canonical form on T star of M, then corresponding operator delta of big omega identically equal to 0. And so all forms which proportional to this big omega, they are in the kernel of this correspondence. So it's not one-to-one. And we need to do something. You will see how we will solve this problem. This problem solved by so-called
So we have a problem. Volodya, can you try to recover your sound? Oops. Volodya, you have to switch on your microphone. We can see your screen, but you have to switch on your microphone. Okay, let us.
how long? Because I've lost the connection, and I don't know when I have lost it. Is it okay?
Okay, right here. You can continue.
Okay, so if we consider symplectic vector space V and dual space V star, and consider any K form on symplectic vector space, then this form can be uniquely decomposed into the finite sum of the following forms. First of all, we have so-called omega 0. It is the form of the same degree, but if form omega, we don't suppose that it is skew orthogonal. And then we suppose that the form omega 0 should be skew orthogonal, but the same, of course, there are some other part which are not, might be not skew orthogonal. And this part is proportional big omega. Operator big T means wedge product with big omega. Operator T square is a wedge product of omega square, and so on. So the forms omega 1, omega 2, they are skew orthogonal, but they have degree k-2, k-4, and etc. This sum is finite because at some point we, by dimensional reasons, have to stop. And this operator T and this decomposition, it is analog of Hodge decomposition for primitive forms in symplectic geometry. And this theorem is a straightforward consequence of very famous result of any irreducible, any representation can be presented as a sum of irreducible representations. And representation theory helps to prove the theorem in very straightforward way. If we have this symplectic vector space V star, dual symplectic vector space, then we have natural action of SL2 on exterior algebra of this vector space. And this action defines by multiplication with canonical two form, which we denote by big T, dual contraction with a canonical bivector, which people usually denote big T inverse. It means top and bottom operators. This is top operator and bottom operator to multiplication with the contraction bivector. Take their commutator, give scalar operator. This is a triple of SL2 representation. So SL2 is realized like exterior multiplication with omega, contraction with dual bivector, and commutator gives you E.Cartan operator, which is scalar and multiplies any form of degree k by n minus k, where n is half dimension of this symplectic space. So this representation of SL2 in exterior algebra can be by Weil theorem developed in this sum of irreducible representations given by operator T, which is plays a role of in this triple multiplication with omega, plays a role of upper triangular E.Cartan operator E. So if we have this representation, and we have it always, for any form omega, we have so-called effective part of sub-zero. And this effective part is exactly the part which is responsible for definition of Monge-Ampère operator in unique way, because all other part of omega, they depend on a big canonical omega, and after restriction to the graph of some differential of some function, this part gives you identically zero. So Monge-Ampère part defines only by omega effective, omega zero. And then it is important ingredient of Lepage and Lychagin observation. We have two different effective K form, which vanish on the same isotropic K-dimensional vector subspace in our symplectic space V. Effective two forms are proportional, and this gives you unicity of correspondence. Now, we can restrict our attention primitive in Hodge sense n form. Okay. I didn't say you that equation, Monge-Ampère equation, top form, it is form of half n, but can consider also form n minus 1 and etc. And we will obtain all interesting differential equations, but they will not top degree. First order equation, for example, you can represent in this way as well. Interesting, of course, when k equal to n, half dimension of T star. So what is the solution? What's the advantage of this approach? Advantage of this approach that we understand that it is not necessarily consider only classical graphs which well projected to Q or X subspace, but also we can consider any smooth Lagrangian submanifold in T star. And we say that generalized solution of Monge-Ampère equation, it is a Lagrangian submanifold in T star which in the same time is integral manifold for our form omega. So our form omega, we don't need to restrict only on differential of some function, but we can restrict it on any Lagrangian submanifold in T star of M. And such Lagrangian submanifold we will call generalized solution. Of course, this approach has some advantage and some disadvantage. Locally, any such generalized solution looks like a graph of one form df for some regular solution or classical solution f. But globally, it is not uniquely univalued. It's multivalued, and it was the first observation, maybe not very how to say hard, but it in the framework of Vinogradov's approach to nonlinear equation, it was a very nice example of his philosophy of so-called R multivalued solutions. You can easily imagine this generalized solution like Lagrangian submanifold, which is skewed from different pieces of regular solutions. So this is a regular solution df. Then we have up some singularity, which is projection singularity. Then we have again classical solution, which is given by function g. Up here we have again a singularity, and then classical solution given by h. So important ingredient of this theory, of course, the theory of so-called Lagrangian projection singularities, which were studied by Arnold and his students. And specific property of this Lagrangian singularities was remarked, and it is really a fantastic observation, was observed by British meteorologist, mathematician, consider these Arnold Lagrangian singularities like singularities
Sorry.
I don't understand what's happened.
Volodya, you can share your screen again.
I share.
Yes, but we cannot see.
Me too, I don't see it. It's a connection, I think.
Yes, we understood it. Okay,
Now,
okay, we can see.
do you hear me?
Yeah. Yes. Okay. You can.
So it was,
continue.
and very interesting results you will hear in this framework in the next talk of Roberto D'Onofrio. He will speak about the singularities more deeply. Now, I will speak about the application I mentioned in my introduction. This application is so-called classification problems. This application is based on the following very natural definition. If we have a local symplectomorphism of T star of M, which I denote by big F, then we say that two symplectic Monge-Ampère equations are locally equivalent if the corresponding forms transform one to another. And of course, if we have a generalized solution of one of these Monge-Ampère equation, then the image of this Lagrangian submanifold gives you generalized solution of the first Monge-Ampère equations. If you have two Monge-Ampère equation and local symplectomorphism, which transform one form to another, then solutions of one of this equation transform to the solution of another. And this gives you a very, very powerful how to find solutions of this nonlinear equation, explicit solutions. And this is what people call Legendre transformation, or partial, more precisely partial Legendre, because I will not use the full Fourier rotation. I will use only half of it in 2 dimensions. This partial Legendre transformation graphically shows you the following. Let's consider the Monge-Ampère equation, nonlinear equation, in right-hand side. V, it's a determinant of Hessian equal to 1. V is unknown function, and then this equation is written with the help of the form dp1 dp2 minus dq1 dq2, like I explained in first part. And then this equation, if we have Legendre transformation, which Legendre transformation means that we keep in our space coordinates q2 and p2, and we change coordinates p1 and q1 with change in sign in such a way that this half rotation preserves symplectic structure dp1 dq1 plus dp2 dq2. Then this form goes to the form dq1 dp2. So you see dp2 we don't touch. Instead of p1 we put q1. Instead of q1 we put minus p1. q1 was here in the first place, and here we put it on the second place. It means that we change sign q1 minus p1. What's the form we obtain? We obtain the form which corresponds to Laplacian equation. Laplacian equation is linear equation, and we know that solution of this equation easily get taken any, for example, harmonic function, and from this harmonic function we can find, for example, here you see this function eq1 cosine q2, and then the transformation which we used here, rotation, transform Lagrangian submanifold given by this function eq1 cosine q2 to the Lagrangian submanifold, which is given by function q2 arcsine q2. It's very easy to compute, and this function gives you solution of nonlinear equation, explicit solution of this nonlinear equation Hessian equal to 1. It's of course a toy model, and but you have the idea how you can use transformation, symplectic transformation, to solve. It's a change of variables, in fact, but it is symplectic change of variables to solve explicitly nonlinear equation using solution of linear equation. And on this idea is based our approach to theoretical meteorology, important so-called semi-geostrophic 3-dimensional equation, which was studied by British meteorologists. This equation has the following nonlinear form. The determinant of 3-dimensional Hessian equal to determinant of 2-dimensional submatrix 2 times 2, which depend only on derivatives over x and y, and on z you have a d square of u plus dz2. This equation, these people very carefully studied numerically. And you see this graph of this solution. In this graph, definitely you can see the appearance of the singularity here. But we can also propose the following explicit solution of this equation. We can write this Monge-Ampère equation corresponding to effective form in 3 dimensions. This effective form in canonical coordinates is written like dp dq dz, dx dy dr. R is a third coordinates which is dual to z, minus volume form with the coefficient, some coefficient gamma. This coefficient sometimes very important in meteorology, but I want to say that this form, it is exactly the effective part of the form which correspond to a nonlinear equation on the previous slide. And then we can see that this form can be represented as a sum of 2 decomposable forms, dp dq dz and dx dy times dr minus gamma dz. You take the symplectomorphism applying to these 2 decomposable forms. This symplectomorphism is quite simple. It also looks like a partial Legendre transformation. And then you obtain reduction of this equation to symplectic equation with constant coefficients, Hessian in 3 dimensions equal to 1. And this equation, of course, we are able to solve explicitly. For example, this exact solution of this equation is given by this function through this integral. Or geometrically, this solution is given by the Lagrangian submanifold in R6. And this Lagrangian submanifold, it's depends on this function alpha, which looks, it is this root of degree 3 from this rational function of x, y, z. It is very, very interesting that independently such type of solution was obtained many, many years after in papers of Yao and his collaborators. And they discovered a huge amount of such solutions in different contexts, not meteorological context. But now I want to discuss another interesting application of this symplectic diffeomorphism and symplectic equivalence, which is also relates to meteorology, so-called Hoskins geostrophic coordinate transformations. So this semi-geostrophic equations, they come from so-called Boussinesq primitive equation. It's an approximation of Boussinesq. And then, of course, you should take into account so-called Coriolis force, because our Earth is turning around the X, and the all meteorological systems, they come from Navier or Euler type systems, including the Coriolis force into account. So after some theoretical considerations, Brian Hoskins proposed a change of variables to a system of semi-geostrophic equation, and fantastically, this Hoskins geostrophic transformations, it is exactly a kind of our symplectic change of variables. It was our observation with Jan Rulston maybe 20 years ago. We discovered that this transformation, it is just a kind of symplectic diffeomorphism in Monge-Ampère operator context. And the corresponding Monge-Ampère operators can be reduced and can solve a huge amount of very important in meteorology equations which are all reduced by such type of transformation to the equation Hessian equal to 1. And you see that we know how to solve it, at least in some special case. So this equation, for example, equation 3, it's a typical geostrophic 3D equation. So you have this Laplacian, you have this Hessian of 2 times 2 submatrix, and you have just a derivative. It is also an equation of Monge-Ampère type, and after Hoskins transformation, this equation can be transformed to the equation Hessian equal to n, when n is a constant which important in meteorology. So you can made some simulation using this solution of Hessian equal to 1. I think that maybe more precisely how it works in meteorological predictions or weather predictions, you will hear in talk of Professor Rubtsov. So this is another 3D type equation which can be reduced to Hessian equal to 1 by Hoskins. We have 3 classes of such equations. This corresponding forms, anyway, and this is corresponding symplectomorphisms. So again, I repeat that Hoskins' discovery, it was nothing but symplectomorphism of phase space in Monge-Ampère structure theory. And the equation, final equation, as I told you, is Hessian equal to constant. Now, a few words about Sophos-Lie problems after this symplectic equivalence. So in 2 dimensions, you have the following table of Monge-Ampère equation with constant coefficients. The only symplectic invariant of 2-dimensional Monge-Ampère equation is Pfaffian. And the Pfaffian for Monge-Ampère equation might be, after some normalization, considered like a constant equal to 1 or minus 1 or 0. If Pfaffian equal to 0, we have degenerate Monge-Ampère or parabolic case. It is not interesting from the viewpoint of geometry. In fact, it is interesting, but it is another kind of geometry. But if Monge-Ampère is non-degenerate, it means that Pfaffian non-zero, then both equations are well known. This is Laplacian and wave equation. And geometrically, it means that we have 2 interesting structures. I will go to this in a few minutes. In 3 dimensions, if you have 3 form, we have no more such invariant like a Pfaffian. That's why the solution for dimension 3 was much more interesting than in dimension 2. We discovered with Valentin in 1983-86, we discovered the following invariant, which is a symmetric tensor G sub omega, and this symmetric tensor, our colleagues now called Lychagin Rubtsov metric, but it's a little bit strange for me because it's very, very funny construction. You take your form, it is 3 form in R6, you contract it with the vector field X and vector field Y. So you have 2 form, wedge 2 form, you have 4 form. You multiply it by omega and reduce to the volume, symplectic volume omega to 3. So you obtain some symmetric, because it's 2 forms, symmetric tensor G sub omega. If you introduce to this symmetric form application A sub omega, which we called Hitchin tensor, because Hitchin considers similar things in his approach to functionals in 6-dimensional space, and taking the trace of square of this tensor A sub omega, then we called the invariant, which we called Hitchin-Pfaffian. Of course, it is nothing with real Pfaffian. It is just by analogy of the Pfaffian, which we get in 2 dimension. We called the trace of A square by Hitchin-Pfaffian. And this Hitchin-Pfaffian is the invariant which solves the classification problem in dimension 3. And in dimension 3, we have the following list of all effective Monge-Ampère form and operators. First of all, we have 3 nonlinear orbits, and these 3 linear represented by operator equal to constant, special Lagrangian, and analog of special Lagrangian, but instead of Laplacian, we have this wave operator. Then we have substratum of linear operators. Of course, it is a degenerate from the viewpoint of Hitchin. And to split these 3 cases, Hitchin-Pfaffian equal to 0, but there is also a signature of our metric Q sub omega. It's a quadratic form which obtained from our tensor G x omega xy. And signature of this quadratic form precise the difference between, for example, special Lagrangian and pseudo special Lagrangian. And also it is difference between 3 linear, 2 linear, degenerate, and degenerate 2-dimensional. So full classification of effective forms gives you full classification of Monge-Ampère operators. Okay, now I think I have 15 minutes, and I want to say a few minutes also about how this approach relates to so-called 2-dimensional version of special, of this meteorological system, 2-dimensional version of meteorological system, which also includes a version of semi-geostrophic system as a special case. This approach gives you full bunch of possible Monge-Ampère equation if you consider hyperkähler structure, which we described with Jan Ralston in 2 papers. And this hyperkähler structure comes from the possible circle of models. Circle because, you know, if you have 4-dimensional space, in 4-dimensional space, you have quaternionic triple. And this quaternionic triple you can also parameterize by 3 parameters. And these 3 parameters gives you a so-called twistor sphere. Any combination of I, J, and K with coefficients A, B, and C gives you again a quaternionic type operator if A square plus B square plus C square equal to 1. So it's a so-called twistor 2-dimensional sphere. If you apply similar construction to 3 Monge-Ampère, obtain interesting situation. So you have elliptic Monge-Ampère equation with constant coefficients, which in these coefficients they correspond to so-called flat balanced model of Jan Ralston and his collaborator Mike McIntyre. And among these flat models, you have semi-geostrophic model, which correspond to the choice of the constants in our triplet. And then we have so-called Salmon L1 dynamics. And then we have a little bit strange dynamics of McIntyre and Ralston with this condition of the constant. So classification theorem in 2D gives you classification of all almost balanced models, which have so-called union potential vorticity. This union potential vorticity, I want to confess that it is the condition of constant coefficients, because our theorem for classification works for constant coefficients. So interesting non-uniform potential vorticity models we are unable to classify. Now, I promised to say about geometric structures, why geometric structures are so important in. Let's come back to case between forms omega, now omega small form. We can put the field of endomorphisms, and this field of endomorphisms has very nice property. Namely, if we normalize this endomorphism tensor and introduce tensor big J sub omega, which is our endomorphism divided by square root of module of Pfaffian. So it's non-degenerate case means that you have non-zero Pfaffian, and it means that your Pfaffian in some neighborhood of this point keeps a sign. So you have or -1 or +1, and then taking square root, you need to take module. So such tensor defines in any case, in both cases, if you have 1 or -1 for Pfaffian. So if Pfaffian positive, then you have G square equal -1 from this condition. And this means that your Monge-Ampère operator gives almost complex structure tensor G sub omega. And if you have Pfaffian negative, then J square equal to 1 from this condition. And you have an almost product structure. What's the condition of integrability for this structure? In fact, it was our theorem with Vladimir that following assertions are equivalent. So if we have equation, Laplace equation, or we have wave equation, these two equations are describe integrability of the corresponding tensor. If my form omega can be reduced to Laplacian, then this almost complex structure is integrable. If it is reduced to Hessian, to the Lambertian, then almost product structure is integrable. So integrability of this structure depends on integrability of my equation. And for any omega, this integrability means that the form omega normalized by square root of module Pfaffian is closed. So the integrability condition here for plus or for minus both gives you closedness of this form. And this is nice geometric interpretation of Monge-Ampère structure in 2 dimensions. Then I also want to mention more interesting geometric structure in 2 dimensions as well. So let's introduce so-called current bracket. Current bracket, it is a bracket on the tangent bundle of M plus cotangent bundle of M. So it's bracket between vector field plus 1 form and vector field plus 1 form. By definition, it is gives you natural interior product on the direct sum, this one. And current bracket defines by bracket, which is the sum of brackets of vector fields, and also additional terms, which comes from Lie derivative of second 1 form along the first vector field minus first 1 form along the second vector field. And also plus minus half of the differential of the following function. You have contraction x first and second, you have a function. You have contraction y and psi, it's also a function, and then you have differential. So you obtain some operation, and this operation is, it would be a nice operation, but there are some no. No, it means that this operation is not a Lie bracket. And Nigel Hitchin used this to give the definition of so-called almost generalized complex structure. Namely, using this bracket, he introduced a notion of integrability of the following tensor. Let's consider big fat J from T plus T star, such that J square equal -1. And with respect to the natural pairing, it is skew-symmetric. So I told you that there is a pairing, this inner product, and this, with respect to this inner product, it's skew-symmetric. Then we have some almost general, but if we have a current bracket, we can introduce the notion of integrability. Namely, if we have a eigenspace, because G square equal -1, so we have splitting of T plus T star in two eigenspaces. And if the space one of these eigenspaces is closed under the current bracket, then we say that this almost generalized complex structure, What is the relation with Monge-Ampère? This relation was discovered by Bertrand Bannos, and it is the following. If we have a Monge-Ampère equation with some effective form omega, we can add to this effective form non-effective part mu times big omega. This form omega prime is no more effective, but it has another good property. We can make such a choice of mu, function mu, that this form omega prime corresponds to an operator of divergent type. And then Bannos proved that if we have a divergent type Monge-Ampère operator and the corresponding effective part of this omega is closed, you can add this such omega prime should be closed as well. So then generalized complex structure G sub omega, which is built with the help of our tensor A sub omega. You remember we have this A sub omega. Then we can consider this block operator. In diagonal, we have A sub omega minus A sub omega dual with respect to this duality. And then here we have operator which corresponds to omega -1. And here we have this operator 1 plus A square omega times it doesn't, you see, omega is any, so it is not 0 because it A square neither -1 neither 1, it is any. And we have this tensor, and this tensor is integrable with respect to this current bracket. So integrability of this tensor is equivalent closedness of this divergent type form. So integrability of corresponding Monge-Ampère corresponding integrability of this almost complex structure. As a result, using the Marius Kreinik observation, we can obtain geometry of the following generalization of Monge-Ampère equation. Namely, let's consider so-called Hitchin pair. Hitchin pair, it's a pair of two bivectors, pi and big pi. One of them, big pi, say non-degenerate, so it's inversion of symplectic. And we suppose that they are not necessarily Poisson symplectic bivectors. Means that certain brackets of pi and big pi, they are equal, but not necessarily equal to 0. But between them, they commute. So just for those who don't remember what is cotangent bracket, it is the natural superalgebra structure in exterior algebra of polyvector fields on the manifold. So this polyvector fields, exterior algebra of polyvector fields, admit super Lie bracket, and this super Lie bracket is called Schouten-Nienhuis bracket. This bracket between two vectors gives you 3 vector. So because it acts from k polyvectors and L polyvectors to k plus L minus 1 polyvector. So these vectors, they are equal, and this 3 vector is identically 0. I remind you that if P times P and big P times big P equal to 0, it means that they are Poisson. Non-degenerate means symplectic. I told you symplectic, but it is only if it is Poisson. Generally, it is just non-degenerate, that's all. Proposition that Kreinig proved that there is one-to-one correspondence between such Hitchin pair and generalized complex structure of the following way, of the following type. You have A minus A square on diagonal, P sub A, and sigma on codiagonal, where sigma is inversion of P, which is non-degenerate. A is a composition of small p and big P, which is also big P minus 1, which is also correctly defined. And P sub A, it is P times minus 1 plus A square. So it's a similarly to Bertrand's Banot's construction, you can construct generalized complex structure from Hitchin pair data.
Volodya, I'm sorry.
What?
Volodya,
Yes.
Hitchin pair is the same as the Poisson pencil.
Sorry?
Oh, no, no, no.
The difference is the Poisson bivector.
The difference, what do you mean difference?
Big pi minus small pi.
But they are both
No,
not Poisson. Roughly, generically, they are not Poisson. P times P, not 0, neither big nor small.
No, big pi minus small pi. Am I right that it is a Poisson bivector? The difference.
Yes.
So it is the same as the Poisson pencil.
Difference, yes, because difference, yes, because if
No.
you have
Why?
I don't believe so.
Why?
Well, you square
well,
it.
anyway, you know,
get just
if you
pi,
have
twice,
combination,
that's all. You don't get anything else. If you square a difference.
Okay, excuse me for interrupting.
no, probably not, because you know, if you have combination, it is not necessarily Poisson. It is special condition. You see, if you have Poisson and linear combination of Poisson is not always Poisson.
But this Schouten bracket is bilinear operation on bivectors.
Yes, but
If you multiply by square root of minus one of them, then you probably get Poisson as the sum of it or a difference, but not otherwise.
yeah, no, Dima, if you have Poisson and Poisson, it is not always combination, it's Poisson, of course.
Yes, yes.
Not any linear combination of two Poisson structures is possible, because it
Okay.
also some
Okay. So there is
condition.
only one.
So here,
Poisson.
of course, under some condition, it might be Poisson, P minus small p, but not, I don't see that it is immediately.
It is a pencil, but the only one
Anyway,
that is Poisson.
my observation, it means what we did with Bertrand is the following. If we have now two forms, omega and big omega, which are not necessarily closed, just two forms. And we have between them, of course, this tensor A, our field. Then we can generalize Lagrangian surface. It means that it is closed under A, and also it is in some sense B Lagrangian. It means that these non-closed two forms, they vanish on this L. Locally, this such L you can define by two functions, U and V. And these two functions satisfy to the following first order system of first order partial differential system. So you have a linear part and you have nonlinear part, which is determinant of Jacobian f with respect to x and y. Sorry, Jacobian f, it means uv vector. So you have two first order equation, and this system, which is called Jacobian system, it is interpolate between Cauchy-Riemann, because it's a partial case of Cauchy-Riemann, which is linear, and between Monge-Ampère equation. You can get from this system Monge-Ampère after some reduction. So this system is called Jacobi system, and this is exactly what is differential equation meaning of Hitchin pairs. Namely, Bertrand proved that if we have such system, we can construct two forms and tensor, and these two forms gives you Hitchin pair in sense of Kreinig. And integrability of Jacobian system, it is integrability of this generalized complex structure. It was Banot's observation. And I will finish my talk with the answer what's happened with geometric structures in 3 dimensions. You remember this table of 3-dimensional forms. I will restrict my attention only on most interesting nonlinear 3 cases. The first definition, it's so-called generalized Calabi-Yau structures, or more precisely, almost Calabi-Yau structures. So we have 6-dimensional manifold, which basically is T star of X, where X is 3-dimensional. And we have a quintuple of objects, a metric or pseudometric on this manifold, two form, omega, A, some tensor, and pair of 3 forms, alpha and beta. So G is a pseudometric, omega is a symplectic form on this 6-dimensional manifold. A, it's a endomorphism, which is in square plus or minus 1, and such that this endomorphism interpolate between our tensor G and form omega, vectors U and V, and decomposable 3 forms, such that if you take the product of these 3 forms and reduce it to the symplectic volume with respect to big omega, that this is a constant. Such thing we will call almost generalized Calabi-Yau structures. And we call this generalized Calabi-Yau structures not almost, but integrable if these 3 forms alpha and beta are closed. So what's the relation with Monge-Ampère equation? With Monge-Ampère equation, we have the following. If we have non-degenerate Monge-Ampère structure in 3 dimensions, then this non-degenerate Monge-Ampère structure defines generalized almost Calabi-Yau structure, where our quadratic form, which people call Lychagin Rubtsov metric, it's Q omega, big omega A omega and alpha beta gives by this invariant. This is a Hitchin invariant. G is, for example, if you take example of one of three main non-linear Monge-Ampère equations, this is special Lagrangian. Its special Lagrangian gives usual Calabi-Yau structure of C3, which relates to Kähler calibration. Here, pseudometric is just minus dx squared plus dy squared. Tensor given by this one form with values in vectors. Canonical two form in 6 dimensions. And forms alpha and beta, it is just 0, 3, 0 and 0, 3 holomorphic forms on C3. So this is a canonical Calabi-Yau structure of C3. More interesting if you consider pseudo special Lagrangian. This pseudo special Lagrangian gives you by the following quadratic pseudo form, I mean pseudo metric, and then this tensor field A, again canonical omega, and again holomorphic and anti-holomorphic 3, 0 forms in C3. And Hessian equal to 1 gives you so-called a real Calabi-Yau structure, or just Hessian Calabi-Yau structure with the form, with a metric G, which is a just degenerate. You see, it is a natural 3,3 metric, and then A corresponding tensor, corresponding canonical form, and alpha and beta, they are real decomposable forms instead of DZ, DZ1, DZ2, DZ3. They are real part and the imaginary part, if you want. So this is a pseudo or Hessian Calabi-Yau structure. And theorem, which was based on our classification theorem, is the following: that symplectic Monge-Ampère equation in R3, which associate to effective form omega, which is non-degenerate, locally equivalent to one of the following equations: Hessian equal to 1, special Lagrangian, or pseudo-special Lagrangian. And integrability of this equation, it's integrability of generalized Calabi-Yau structures. But it is not enough that in integrability in algebraic sense. You also should check that these Calabi-Yau structures locally flat, because in dimension 3 there is also, in integrability there is also condition of some curvature tensor nullity. So it's the most new result here is appearance of some abstraction to integrability in terms of curvature tensor for corresponding metric. So the metric should be locally flat. So to finish my talk, I just say that what I didn't tell you. I didn't tell you about how to compute symmetries, conservation laws, and Noether theorem, variational calculus, self-similar solutions, except what I showed, this toy models, shock waves, and so on. Divergent Monge-Ampère and appearance of Euler-Lagrange operator. Also interesting, the structure of corresponding Vinogradov non-holonomic spectral sequence in Monge-Ampère context. And also, I didn't tell you about links with this Calabi-Yau 3-dimensional structures and Monge-Ampère Lie and current algebroids, which we introduced with Yvette Kosman-Schwarzbach. Things like linearization of coupled Monge-Ampère, you will see probably in the next talks. Lagrangian Monge-Ampère Grassmannians and characteristic classes. I talked about this in Yaroslavl seminar once, and probably it is possible to find, but I can once speak about it. And many other interesting things you will hear in the next talk of Roberto, Jan, Martin, and Lewis. Thank you for your attention. This is a bibliography which I use, only bibliography based on our paper, my paper. It is the lectures on Monge-Ampère structures in this book, and our book with Valentin and Alexei Kushner, from which I took this Eureka cat.
Yeah, thank you very much for a talk. And questions or comments? You're welcome.
I'm sorry for interrupting you earlier, Volodya. I just was a little bit interested in this. I was very interested in that pair of bivectors. They look pretty much like the bivectors you use in so-called Leonard-Magritte induction. So I just wonder whether anything like that exists for this couple of bivectors, and whether this has something to do with Monge-Ampère equation, maybe.
But they are not. They are not
Poisson, right?
They are not Poisson, but this, you know, what they do. They play the role of integrability condition for so-called Jacobian system. I want to say just before any questions that it is very difficult, and I don't know how to write the corresponding Jacobian system in dimension 3. You see, in dimension 3, we have also some geometric structures, and we have also some current brackets probably for Monge-Ampère algebroid, which correspond to this generalized Calabi-Yau. But we don't know how to write the corresponding general Jacobian system, the corresponding integrability condition. If we write proper Jacobian system, of course, to write integrability condition is possible, but how to write it in general, like here, you see here, you write for any Jacobian system, you can rebuild some generalized complex structure, and to prove integrability using this Kreinic result. But how to do it for any dimension, I don't know. It is
that was for dimension.
problem.
For what dimension? That what was it? For dimension 2, for dimension the Kreinic results. I mean, for what dimension
Yes.
was it? For dimension 2.
But it's for dimension 2.
Okay.
Kreinic result is general for any Hitchin pair, but
I see.
in application to Monge-Ampère pairs or Jacobian system, it is only in dimension 2, because I don't know the analog of how to write Jacobian system in dimension 3. It looks similar, but if you write, you will see that it is not so easy. There is a discussion in Math Overflow with Robert Bryant about possibility to write, and it is not so naive. Of course, you can write something, but not so naively straightforward.
I see. Thanks.
I think it is interesting as a question to PhD student. It's a good question to study.
Volodya, could you say if it is natural to study the discrete version of Monge-Ampère equation, and the same question for the non-commutative version? Are there some examples, some pretty examples of such version of the Monge-Ampère equation?
I thought about it, because of some experience in non-commutative equations. I thought about if it is possible to write first of all, there are two naive approaches to non-commutative Monge-Ampère. First approach based on the star quantization, of course, the star deformation. You just consider instead of well, consider just kind of Moyle type construction. Probably it is possible, probably. And also I tried to think about quasi-determinant of Monge-Ampère type, but I didn't succeed finding about discrete Monge-Ampère. I was thought about it. Sorry.
For the
I just don't know.
for the non-commutative case,
I mean, you can replace derivatives by discrete derivative, but I mean discrete different by difference. I don't know. I don't know. I never saw any results. I don't know.
so my first idea for the non-commutative version is that it is related with the Poisson-Lie groups. Could it be
It's only groups.
relevant?
This, you know, this is our theorem with this naive theorem about Monge-Ampère equation with constant coefficients. It is of course the simplest case when Monge-Ampère equivalency with respect to translations. You see, you have a now. Let's consider the next step, probably to consider Monge-Ampère forms. I mean, this geometric approach, instead of invariant of translation, consider just equivariant forms. So you consider Monge-Ampère on some homogeneous spaces. This globalize it and consider Monge-Ampère on some homogeneous spaces from the viewpoint of classification, from the viewpoint of, but I don't know.
Okay.
I didn't do it.
Thank you. Thank you.
Okay, any more questions or comments? So if not, I would like to thank speaker again. And thank you for your attention. I believe we will see you next week. Okay, thank you.
Thank you. Bye.
Yeah, goodbye.
Bye bye.
In China, 再见.